Indonesia is the world's fourth most populous country with 270.2 million people and a vast territory that leads to an increased mobility each year. In 2019, it was recorded that the number of motorized vehicles operating on the roads reached 130 million units, increasing by 1.8% in the following year. However, this high mobility correlates with the rate of traffic accidents. In 2019 alone, there were a total of 116,411 traffic accidents, averaging 318 cases per day. Based on this fact, Indonesia needs a quick and efficient system to handle road management and repair. So far, the government has made efforts to quickly repair damaged roads, one of which is by launching an application for the public to report and map the condition of damaged roads. However, this application is still inefficient as it relies purely on public observation, undermining its precision and accuracy. Therefore, I, Arya Primavista as a software engineer, I, Pandekade Kresna Juliana as a hardware engineer, and I, Muhammad Harish as a data engineer, has made a system that can detect and map road damage automatically. This system works using the deep learning method integrated with the Internet of Things and a website to process the provided input data. To detect and map road damages, this system uses two main data inputs. The first one is images obtained from a camera sensor, and the second is vibrations obtained from a gyroscope sensor. The hardware consists of several main components, including Raspberry Pi 4B 4GB as the main data processing unit, 3.5-inch LCD screen to display the system interface, Raspberry Pi high-quality camera as image data input, global positioning system sensor to obtain the system's location coordinates, and gyroscope sensor to obtain vibration data from damaged roads. All hardware components are placed in a specially designed casing so that the system can be used easily. The software system is divided into two main parts, an object detection model and a website. The object detection model is built using the convolutional neural network method, which is part of deep learning. To achieve the most optimal model results, the training process used 100 iterations with 592 sample images of potholes for training. Whereas for the system's evaluations, we use 148 image dataset. Based on the analysis using the YOLO V5 algorithm for model training, the results obtained were a precision rate of 0.832, a recall rate of 0.857, and MAP or mean average position of 0.893. These results indicate that the model's performance is very optimal. The website functions to present the road damage detection results to users, whether it be government agencies or the public, so that they can immediately respond to the road damage points. The website of the RoadSense system consists of two main pages, a mapping page and view page. The mapping page is used for real-time detection to see the system's condition during the mapping process, whereas the view page is used for viewing mapping results obtained periodically. One of the advantages of the RoadSense system is the computation process using edge computing. With this method, bandwidth and latency can be minimized, so that without sending data to a server, pothole or road damage locations can still be detected even when the system is not connected to the internet. The RoadSense system works as follows. First, the user activates the system and enters mapping mode. Once active, the system begins mapping the road by activating the camera and gyroscope sensors, followed by activating the machine learning model. When the system detects a pothole or road damage, the GPS sensor takes the coordinates and sends them to the database along with the captured image. The data is then sent to the website so that road damage points can be followed up by the government and relevant parties. To determine the accuracy of the RoadSense system, conducted on a road from South Jakarta to Bogor, covering a distance of 62.8 kilometers. The analysis found 242 road damage or pothole points, with 214 being crack detections. Based on the calculations, the system achieved a final accuracy score of 0.884 or 88.4% accuracy. This shows that the system has great potential to be implemented in the field because it has high accuracy, ease of use, effectiveness, and efficiency. With the RoadSense innovation, the government can maintain road infrastructure quickly and efficiently with an accuracy rate of 88.4%. It is expected to be implemented in the long term with cooperation between government agencies, especially the Ministry of Public Works and Public Housing, and the public to address road damage issues quickly.